Hello students, now we reached chapter 15. The topic is redox titrations. So in this chapter, you will learn how the redox titrations uh, are being done. Okay, and after you successfully studied this chapter, uh, you will have a very powerful weapon. Okay, uh, in studying not only chemistry but also in other fields like biology, biochemistry, and physics and environmental science and so on. Okay, so this chapter is very important. As I mentioned earlier, four chapters are devoted to um, electrochemistry. Okay, and the four chapters are devoted not only this electrochemistry but also to acid-base chemistry and to separation techniques. Okay, so those three topics are the essentials of chemical analysis. Okay, so you very carefully follow me. Yeah, and then this book, this quantitative chemical analysis, this book very well describes the redox electrochemistry. Okay, okay, let's start. The front page of this chapter now introduces high temperature superconductor, okay, and its analysis. As you know, the superconductor is the material that have no resistance. Okay, it's amazing, and that phenomena was discovered a long time ago, more than 100 years ago. Okay, and it was very an accident that this superconductivity was found in liquid mercury. Yeah? When lower the temperature, yeah, more and more, and then someone, I forgot the name, uh, this he found suddenly mercury resistance is gone. Okay, and he named it superconductivity, which means there is no, absolutely no resistance. Okay, and it happened below liquid helium temperature, right? Quite low temperature. Liquid helium temperature is 4 Kelvin. Okay, it is very near to the absolutely zero Kelvin, right? And liquid helium is very expensive. So although that phenomena was discovered, it was quite difficult to apply the phenomenon for the practical things, right? But even since ever since, many people studied superconductivity and they raised the temperature. Okay, that they raised the superconductivity temperature, which is called the critical temperature. Okay, usually superconductivity is observed below a certain temperature. Yeah, the temperature is called critical temperature. Okay, but the critical temperature was too low. Okay, it was too low, so maybe several kelvins, and or maybe it's just over the 10 kelvins. Yeah, so the temperature is so low, so in order to use that for conductivity, you have to lower the temperature with liquid helium, right? Yeah, still maybe still so, but there was a breakthrough in 1986. Okay, and two physicists in IBM research lab in Zurich, Switzerland. The Georg Bednolz and Alexander Müller, they found the same superconductivity in metal oxide. Okay, yeah, like this one. Okay, yttrium, barium, copper oxide. Okay, this is kind of inorganic material, not metals. Although it contains three different kinds of metals, but actually it is like a stone. Okay, but when they load, okay, when they load uh, the temperature below the liquid, let me see, then they lower temperature with the liquid nitrogen. Liquid nitrogen boiling point is 77 Kelvin, and then they found suddenly uh, the uh, the resistance of this material was gone, right? So the people called it high temperature superconductivity, yeah, and then those materials are called high temperature superconductors. Okay, so in 1987 they were awarded Nobel Prize in Physics. All right, and since liquid nitrogen is really cheap, very cheap according to the liquid helium. So that time it was said that almost half of physicists in the world, yeah, turned to study this high temperature superconductivity. Okay, and much progress has been made since then. But since this is not a metal, it is a kind of inorganic material, yeah, oxide. So although the critical temperature is quite high, but problem is that it is very difficult to process this material. Now, for example, it is very difficult to make it into a thin wire. Okay, think about that. Can you make the thin wire with from in a stone? Yeah, it is not easy at all, right? Okay, so unlike the earlier, the hope, is application, yeah, is not so wide. Anyway, it was a breakthrough, yeah, in physics, right? But how this high temperature spot conductivity is related to electrochemistry? Look at this one. Yeah? This is so-called 1,2,3 compound. Right? Yttrium, is stoichiometry is 1, barium is 2, and copper is 3. Okay, and there are oxygen atoms. Yeah? Here 7, maybe less than 7. Yeah, 7 minus delta. Anyway, two people wanted to know the oxidation state of copper, right? It is very important, and it is not easy to determine the copper oxidation state precisely, but electrochemistry can do that. Mhm. Yeah, in our book, and there is an example how, and yeah, I mean there is a demonstration, illustration how this copper oxidation state is determined, yeah, by electrochemistry. All right, and let's give some more word, yeah, to this high temperature superconductor. Look at first this figure. Okay, this a small disk is the high temperature superconductor. Yeah, this the 1,2,3 compound. Yeah, and in the here below, this is the what? This is the magnet. Okay, and then whole thing, this part is cooled down with liquid nitrogen, and very surprisingly, this one, uh, this high temperature superconductor, mm, is you know what below is float above this magnet, right? That phenomena is called Meissner effect. Okay, Meissner effect. So there is nothing in between, right? It floats above this magnet. Yeah? So when a magnetic field is applied to a superconductor, current flows in the outer skin of the material such that the applied magnetic field is exactly cancelled by the induced magnetic field. Yeah? I don't know the details. Anyway, the net field inside the specimen is zero. Yeah? Here, the physicist theoretically derive that in the magnetic field inside this high temperature superconductor is zero. So what is the result? Expulsion of a magnetic field from superconductor is called the Meissner effect, and this one is what above float above this magnet, right? And there is no friction between these two materials. So using people hoped that using this phenomenon, they can make very fast the train, for example, yeah, by removing the friction between rail and train, the wheel, okay, but it has not been realized yet. Okay? Here, the superconductor material losing all electric resistance when cooled below a critical temperature. Prior to this year, actually this year is the Nobel Prize awarded, yeah? But these two men published this phenomenon in a previous year. Anyway, prior to 1987, superconductors required cooling to liquid helium. Okay, but liquid helium is very expensive. But after this year, the people began to use liquid nitrogen. Okay, and here this is copper. It is important to determine the copper oxidation state. But when the structure is like that, when the chemical composition is Y, Pa2, barium 2, copper 3, and oxygen 7, 2/3 of copper is in the +2 state, and 1/3 of the unused state +3. You see, copper has usually two oxidation states, +1, the cuprous state, and +2, cupric state. But +3 state is very, very unusual. So it is very important to determine this copper oxidation state. Yeah? And as you the learn the electrochemistry part here in this textbook, and then you can do that. Even you can do that. Okay, now consider the redox titration. Yeah, redox titration is, in other words, this is potentiometric titration. Okay, as I mentioned in a previous chapter, potentiometry means that you measure only potential and relate the measured potential to the concentration of your analyte. Okay, so there is no current flows, right, in this titration, which is the redox titration belongs to potentiometric titration, where based on an oxidation reduction reaction between analyte and titrant, this redox titration is being done. All right. There are many commonalities between this redox titration and acid-base titration. Yeah? Both show a sigmoidal titration curve. Yeah, you'll see soon. A very nice curve. And instead of monitoring pH in redox titration, you monitor potential change as titrant is added to the analyte. Okay, yeah, all the process is the same, but you need electrodes. You need two electrodes, and also uh, as the acid-base indicators can be used in acid-base titration. Also, there are redox indicators whose colors change depend on the redox potential. Okay, that's the difference. But principle is very similar. All right. So you very carefully follow me. Yeah? The electrochemistry is really, really important in science. Yeah, not only in science and but also in engineering, in every field. Okay, of science, it is very important. The first the topic is the shape of a redox titration curve. Let's consider the potentiometric titration of this one, ferrous ion with ceric ion. This is cerium, right? Cerium has two prominent oxidation states, plus 4 and plus 3. So plus 4 is a very strong oxidizing agent, and which is called the ceric ion. But plus 3, say ferrous ion is not this one. This ferrous ion oxidation power is quite low, okay? And this one, this ferrous ion uh, is oxidation power or reducing power. Maybe reducing power, maybe you're right. Yeah. Uh, Here, ferric, this is a divalent, and the trivalent ion is the called ferric ion. Okay, and it can be used as an oxidizing agent. All right, but this one can be used as a reducing agent. So since the ferric ion oxidation power is quite high, then it can oxidize this ferrous ion. Okay, and now you want to analyze this ferrous ion concentration, yeah, using a redox titration. Okay, and this is quite a simple example. Okay, one electron is involved in this reaction. Okay, one electron comes out of this ferrous ion and uh, goes into this acidic titrant. This is titrant. So you first prepare the standard solution of acidic ion, and then uh, you put that solution into the burette and you begin to titrate. Okay, you begin titration. All right. Although this is quite a simple electrochemical reaction, what actual situation is not that simple. Now look at this figure. In aqueous solution, the acidic ion is surrounded by, these water molecules. Okay, water molecules are now acting as what? As a ligand, as a Lewis base. Okay, so there are 1, 2, 3, 4, 5, 6, 7. Yeah, seven, at least seven water molecules are surrounding this acidic ion, and also there is a hydroxide, this group, yeah, OH, yeah, and then likewise this ferrous ion, yeah. Around the ferrous ion there are at least 1, 2, 3, 4, 5 water molecules, and also OH group here, right? And when you add this acidic ion into the ferrous solution, and then hydrogen here, actually this is water, but this hydrogen atom now transferred from this one ferrous ion, this hydrated ferrous ion, to the hydrated acidic ion. Okay, like that. You understand? Okay, so after accepting this one, okay, this hydrogen atom, this is actually radical, but it takes an negative charge. Okay, negative charge, and it transported to this ion and becomes this one. Okay, uh, yeah, right. So total, the originally is uh, total charge. This is I mean the acidic ion oxidation state is +4, and this one after accepting this one, this hydrogen radical, and becomes uh, oxidation state is a load by 1, yeah, plus the 3 state. Okay, here, but this is actually very quite complicated one, right? So here, um, in this case, in this very simply expressed equation, one electron is transferred to acidic ion, okay, from ferrous ion, but actually it is not electron, but in this case hydrogen atom here. But hydrogen atom now has one electron. Okay, so actual effect is the same as the one electron is transferred. Okay, yeah. All right, but we don't care. Yeah? What whatever the details are, we don't care. Yeah? Simply, we write it this way. Okay, this is actually very in actual solution. Things are very complicated. But if you simply ignore, but you consider the core part, that we can write this reaction like this one. Okay. So titration is being done by this setup. This is quite similar to acid-base titration, or very similar to the complex formation titration. Okay, here uh, in the speaker you put your analyzed solution, right? In this case, ferrous ion in 1 molar hydrogen perchloric acid. Okay, and you add this acidic ion the solution uh, from this burette. So add drop by drop. Okay, and then you monitor potential. Now question is, how do we measure the potential? As I said, in electrochemistry you need at least 2 electrodes. Okay, one electrode is what? Reference electrode. In this case, yeah, we may use the Calomel reference electrode, SCE. Okay, standard Calomel electrode, and the other one is what? Indicator electrode. Yeah, the most commonly used electron indicator electrode is what? This platinum. Okay, platinum wire. You put platinum wire. Well, in the next semester, when you if you take the analytical chemistry experimental course, and then you can do this kind of redox titration, yeah, using a potentiometer, okay, and this electrode. Okay, you are going to use SCE and the platinum electrode. Okay, but be careful. This platinum wire is very expensive. Okay, so every semester I buy platinum wire. Some of them are lost. Okay, well, this electrochemical reaction can be broken into two half reactions. Okay, likewise in this reaction also can be broken into two half reaction. Okay, by the way, this reaction equilibrium constant is extremely high. K is 10 to 16. Okay, so almost this one almost they react, and there's virtually no reverse reaction. Okay, let's consider two half reactions. The first, let's write as usual the reaction in reduction form. This ferric ion accept one electron to become ferrous ion, and ferric ion now accept this electron to become ferrous ion. Okay, and this one from the appendix at the back of your textbook is 0. Standard reduction potential is 0.767 volt, but this one ferric ion it is 1.7 volt. So this one is a very strong oxidizing agent, and it can oxidize. Not this one, okay, but this one, this ferrous ion. Yeah? Now, this ferrous ion is acting as what? Reducing agent. Okay, yeah. Okay, and then this reaction actually occurs. Yeah, this reaction actually occurs in the solution. Okay, although even if you remove these two electrodes and you add the ferric ion into the ferrous ion solution, and this reaction takes place. Okay, no problem. But now we want to measure the potential. Okay, as this ferric solution is added to this solution. Okay, so that's why we use these two electrodes. Okay, and on the this reference the indicator electrode platinum, and then what will happen? By the way, this the calomel electrode, this reaction is all the time is there, right? This is fixed. Yeah, and when chloride ion is saturated, this is E0 value for this one is what? Do you remember? 0.241 volt. Okay, and how the platinum electrode potential is being developed? Okay, since this platinum electrode potential is only one. Okay, it cannot show two potentials at the same time. Okay, which means that, yeah, here we have this one two half reactions, and then we can use any of them to calculate platinum electrode potential using what? Nernst equation. Okay, that's very important. So the total cell reaction can be written by this one. If you use this one, the ferric and ferrous ion, and use this one, this reference reaction, and then you can write this way, or if you use this ferric and ferrous ion reaction, and then you can use this way. Okay, yeah. This is a cell reaction, but this is a titration reaction. They are not the same. Okay, why? Because in the cell reaction, yeah, this is electrochemical setup, and it has all the time the reference electrode, right? So you have to consider this reference electrode reaction, yeah, like that. But in most, the analytical chemistry textbooks, they don't explain this way. Although, yeah, this explanation is very good. Yeah, although it is not easy to understand, at the beginning. Yeah, but try to understand anyway. But since this potential reference electric potential is all the time is the same, so yeah, from now on, yeah, we don't need to consider this way. Okay, we consider only this reaction. And then you will learn how to calculate the potential, this one, potential measured between this indicator and reference electrode. All right. Okay, let's stop temporarily here.